Today we're going to discuss how to add accuracy reporting to an already existing neural network. We're going to do that by starting with a simple neural network that we created in a previous screencast. Here we have a neural network that is learning to classify images from the classical MNIST dataset by using a simple one-layer neural network with a ReLU activation and using gradient descent on cross-entropy. What we're going to do is we're going to take this model, which we can see that it trains here, and we're going to look at the accuracy of the model, and we're going to play around with a few things to see what we can do to make it work better. So here, let's just go over quickly what we have. So here we have a network that has an input variable x and two weight variables, w and b, for the weight and the bias that run them through ReLU activation. We have a variable y underscore that will contain the true labels for each data set, and we run that through cross-entropy to get our loss function. Then, for each step in our loop, we say that we're on that step. We take a batch of data from our data set, and we train a model on that. What we want to do is we want to get an understanding of how accurate our model is. So the first thing that we're going to do is we're going to define a variable that tells us if our prediction is correct or not. We're going to do that by calling the tf.equal function on two instances of the tf.argmax function. And so what this is going to say, it's going to ask us to find the value in our y and y underscore tensors that has the highest value, and then it's going to compare if it is the same index for each tensor. The output of this will then be a 1 or a 0, depending on whether or not both instances have the same value. Once we have that, we're going to calculate accuracy by using the reduce mean function on the output of the correct prediction. First, we need to cast our correct prediction to be a float, as it is currently, I believe, a Boolean. And then once we have that, what that just means is calculate the average or mean over the entire correct prediction TensorFlow. Now that we have this, what we can do is we can calculate our accuracy at each step. What we'll do here is every 10th step, print out the model accuracy. And so to do that, we're going to run our test data set through our model using a feed dict, where here the feed dict is just going to consist of our entire test data set. Finally, once we're done, we want to print out the accuracy of our final model. When you're using your test data set, you have to be careful to make sure that the only operations that you're running don't update your graph, only print out the results. If we were instead running the train step and feeding these variables, our comparison would be inaccurate because we would be training the data on the test data set, which would make it impossible to accurately compare results. Now, let's run our results and see what happens. So currently we have a learning rate of 0.001. Let's start with a rate of 0.1 and see what happens. What we can see is that we have a final accuracy of 0.1714, which is an improvement from the start. So the model starts out at 0.1097, goes after 10 steps, it has an accuracy of 0.14, then 0.16, then 0.1752, and then the final result is 0.1714. That's not very good. For an example, state-of-the-art models on MNIST will have accuracies that are well over 98%. So let's try a few other things. So the first thing that we can try is we can try going up to 100. What happens if we train it longer? That's weird. Our model actually goes down. What I think is happening here is overfitting. Let's go back to where we were before. Let's try playing with another variable. What happens if we have a smaller learning rate? As you can see, we have an accuracy of 0.278, which is just under 0.3. Let's see what happens if we continue to decrease our learning rate. Wow, that's quite good. As you can see, it's very simple to add testing to your model and to get an understanding of how accurate it is and how that actually changes over time.